Hello everyone, we are Group 10. For today's final presentation, we will introduce three top-tier conference papers: Visual Geometry Grounded Transformer, VGGT, Graph Mamba. Generative Pre-Training of Graph Neural Networks, GPTGNN. These works represent major advances in 3D vision, graph sequence modeling, and graph pre-training. I will begin with the first paper, VGGT, the CVPR 2025 Best Paper. Here is today's outline. We will cover the background and motivation, its connection to data mining, the proposed method, performance results, strengths, weaknesses with possible improvements, and finally, 3 questions for the authors. Traditional 3D reconstruction pipelines rely heavily on geometry-based reasoning. Methods like structure from motion and multi-view stereo refine camera parameters and 3D points through repeated iterative optimization such as bundle adjustment. These classical methods have mathematical guarantees but are slow, computationally expensive, and must recompute everything from scratch for every new scene. It treats 3D reconstruction as a data mining problem. Instead of deriving geometry step by step, the model learns cross-view geometric patterns directly from large-scale 3D annotated datasets. In other words, similar to how LLMs mine linguistic structure from large corpora, VGGT mines multi-view geometry from data, turning 3D reconstruction into a pattern learning task. This slide shows the overall VGGT architecture. VGGT is a unified feed-forward transformer that predicts all 3D reconstruction outputs in one shot. The model takes n images as input, converts them into semantic tokens using DINO, and processes them with alternating attention, which mixes global and frame-wise attention. Finally, VGGT outputs all 4 3D components at once: cameras, depth maps, point maps, and tracks. So the traditional multi-stage SFM plus MVS pipeline becomes a single forward pass. Next, let's look at token initialization. Each image is first patchified and converted into semantic tokens using DINO. Then we add 2 types of tokens to every frame: a camera token for predicting the pose, and register tokens to support dense outputs. The key idea is the anchoring mechanism. The first frame's camera and register tokens are initialized differently. This tells the model that the first image defines the global coordinate frame, so all cameras, depth maps, and point maps stay aligned automatically. The core innovation of VGGT is alternating attention. It combines global attention, which captures cross-view geometry, with frame-wise attention, which preserves each image's local structure. By stacking these two repeatedly, the model learns both local geometry and multi-view consistency, essentially learning what SFM and MVS provide, but without any iterative optimization. After alternating attention, the model branches into 2 main heads. First, the camera head, which uses the camera tokens and a simple MLP to predict intrinsics and extrinsics. Second, the DPT head, which converts image tokens into dense feature maps and predicts depth, point maps, tracking features, and uncertainty. Together, these heads output all dense information needed for full 3D reconstruction in one shot. Finally, we look at tracking. The tracking head takes the tracking features from the DPT head and passes them to Co-Tracker 2, which builds correlation maps and finds each query points matches across all images. This gives us consistent 2D correspondences across views, while staying accurate even under viewpoint changes and occlusions. This table compares camera pose accuracy and speed. Traditional methods like COLMAP take over 10 seconds, and deep models like DUST3R and MAST3R still need 7 to 9 seconds. VGGT is a major jump. Its feed-forward version reaches 85.388 AUC in just 0.2 seconds, making it both faster and more accurate. With a BA refinement, it even goes up to 93.5, So VGGT is clearly the fastest and most accurate in this task. This table compares multi-view depth estimation. Models in the top section use ground truth cameras, so strong performance is expected. The key result is in the bottom. Without any camera inputs, DUST3R gets an overall of 1.741, while VGGT achieves 0.382. This means VGGT matches, or even surpasses, methods that rely on true camera poses. It's impressive because traditional MVS heavily depends on accurate cameras, yet VGGT remains fully feed-forward and still delivers high-quality depth. This table shows point map reconstruction quality. DUST3R scores 1.005, MAST3R 0.826, while VGGT improves to 0.709, and even 0.677 when combining predicted depth and cameras. Despite running in just 0.2 seconds, VGGT outperforms models that require global alignment. It also shows that reconstructing points from depth plus camera is even more accurate than predicting point maps directly, one of VGGT's key advantages. One of VGGT's strongest advantages is speed. Processing 10 images takes 0.2 seconds, making it dramatically faster than Dust 3R, Mast 3R, and any pipeline involving BA. Memory usage also scales linearly with the number of frames, making the architecture highly scalable. VGGT is therefore well suited as a real-time 3D reconstruction backbone. VGGT's contributions can be summarized by three strengths. Novelty, first transformer to jointly predict all core 3D attributes in one pass. Soundness, design choices like alternating attention and DPT heads are well supported by ablation. Significance, fast, simple, and effective, enabling practical, real-time 3D applications. However, several limitations remain. 1. The paper lacks direct comparison with classical SFM pipelines such as COLM-AP. 2. The model lacks the mathematical guarantees of traditional geometry and behaves more like a black box. Here are three questions we would ask the authors. 1. Why was there no direct comparison with traditional SFM methods? 2. Besides BA, is there a faster refinement strategy to further improve predictions? 3. VGGT has fast inference but extremely expensive training. Is a distilled or lighter version possible? To conclude, VGGT represents a major shift in 3D vision. 3D reconstruction can now be learned directly from large-scale data rather than solved through iterative geometric optimization. It reframes 3D perception as a data mining problem, learning geometric patterns, structures, and representations directly from data. This positions VGGT as a foundational model for future real-time, scalable 3D understanding.
Next, we present our second paper, Graph Mamba by Chloe Wong et al., published at ICLR 2024. Here's the outline of this paper. We'll start with the background and its relation to data mining, then introduce the proposed method and performance. After that, we'll discuss its strengths, weaknesses, 3 key questions for the authors, and finally conclude paper 2. Let's start with the background and the motivation of this work. Right now, to capture long-range dependencies in graphs, the standard approach is using graph transformers. But transformers have a fatal flaw. The global attention mechanism has a complexity of O(n squared). It leads to 2 problems. First, memory explosion. It can't handle large graphs. Second, excessive computational cost. So, we effectively need a model that keeps a global view but operates with linear complexity. Graph Mamba connects strongly to data mining in 2 major ways. First, it enables efficient extraction of long-range patterns, which is crucial for understanding complex relationships in graph datasets. Second, its linear complexity graph representations make it far more scalable than transformer-based methods. And third, through selective SSM, it preserves informative features while suppressing noise, improving the quality of learned representations. In terms of contribution to the data mining pipeline, Graph Mamba provides higher quality graph embeddings, leading to better predictive performance. Its reduced memory footprint allows us to analyze much larger datasets. And finally, by improving training efficiency, it enables more effective model optimization. Then, let's take a look about the core solution of their work. Graph Mamba's solution is treating a graph like a sequence. There are 3 main steps. First, graph flattening, squashing the complex graph structure into a 1D sequence. Second, node prioritization. This is crucial. Sorting nodes based on importance, placing the key nodes at the very end of the sequence so they can access the full context history. Third, Mamba block. Finally, introducing the Mamba model with its selective SSM mechanism to filter out noises and capture long-range features. Now, let's look at the architecture details. It combines 2 key technologies. First, the model is built on top of the Graph GPS framework. It keeps the MPNN to catch local features, but it swaps out that heavy attention module for the Mamba block. The real innovation is down here, the state space model plus selection. Traditional SSMs are fast at inference and parallelizable during training, but Mamba adds a selection mechanism. Unlike older models that try to remember everything, Mamba dynamically decides what to forget and what to remember based on the current input node. But since Mamba only eats sequences, we need graph flattening. To make this unidirectional sequence model work best, they intentionally place the highly connected nodes, so-called hub nodes, at the very end of the sequence. It makes nodes at the end can see the history of the nodes before them. By putting hub nodes last, they can aggregate information from all their neighbors and capture the best long-range context. Also, to stop the model from memorizing a fixed order, they use permutation during training, randomly shuffling nodes that have the same degree. This makes the model much more robust. Let's take a look about experimental results. In terms of performance, Graph Mamba does great on the LRGB, long-range graph benchmark. Specifically on the peptides Funk and Pascal-Voc SP datasets, it actually outperforms existing transformer architectures and achieves state-of-the-art results. The key advantage is efficiency. On the right, the red transformer curve shows memory blowing up quadratically, while the green Graph Mamba line stays linear. It cuts GPU memory by up to 74%, letting us train graphs up to 5 times larger on the same hardware. In short, it breaks the hardware bottleneck. This research is important because it unlocks large graph computing. For tasks like molecular structure prediction or protein folding, where you have tons of nodes and need to see distant connections, Graph Mamba offers a new paradigm that scales way better than transformers. This research is important because it unlocks large graph computing. For tasks like molecular structure prediction or protein folding, where you have tons of nodes and need to see distant connections, Graph Mamba offers a new paradigm that scales way better than transformers. This research is important because it unlocks large graph computing. For tasks like molecular structure prediction or protein folding, where you have tons of nodes and need to see distant connections, Graph Mamba offers a new paradigm that scales way better than transformers. Flattening a graph into a sequence comes with trade-offs. First, we lose some topological structure when compressing 2D or 3D graphs into 1D. Second, Mamba is unidirectional, so its performance is highly sensitive to how nodes are sorted. For future improvements, we could consider a bidirectional Mamba, similar to BiLSTM, or use traversal-based orderings like random walks instead of simple degree sorting. After studying the paper and implementation, I identified 3 main questions. 1. Sorting strategies. Since Graph Mamba is unidirectional, node ordering strongly affects information flow. So in domains like chemistry, would structure-aware orderings, such as chemical bonds or spatial distance, work better than simple degree sorting? 2. Sparse graphs. For extremely sparse graphs, sparse attention is already efficient. So does Graph Mamba still hold a real advantage in these settings? 3. Task generalization. The model is mainly tested on node classification. But for tasks like link prediction that require fine-grained local interactions, can Mamba's compressed state still capture the necessary detail? Graph Mamba offers a promising way to scale graph neural networks. By flattening graphs into sequences and using the selective state space mechanism, it preserves long-range modeling while keeping near linear complexity, allowing much larger graph datasets to be processed even with limited hardware. It also aligns well with data mining. Its ability to capture long-range patterns, reduce noise, and produce high-quality graph representations strengthens tasks like node classification, community detection, molecular analysis, and anomaly detection. Overall, it provides a scalable backbone for mining larger and more complex graph data.
Next, I will present our third paper, GPT-GNN, Generative Pre-training of Graph Neural Networks, a KDD 2020 work on reducing label requirements in large attributed graphs. Here is the outline for our third paper. I will walk through the motivation, the research problem, its relation to data mining, the proposed method, performance results, strengths, weaknesses, our questions to the authors, and finally the conclusion. Next, let me introduce the background and motivation. GNNs perform well on tasks like node classification, link prediction, and recommendation, but they require large amount of labeled data, especially on million-scale graphs. To reduce this dependency, the authors draw inspiration from the pre-train fine-tune paradigm in language models. The goal is to pre-train a GNN on unlabeled graphs and then fine-tune it for downstream tasks. This is the central motivation behind GPT-GNN. In data mining, this paper connects to major graph mining tasks such as node classification and link prediction. GPT-GNN fits into unlabeled graph representation learning and self-supervised embedding, since it learns directly from label-free graphs. It also enables cross-domain and cross-temporal transfer, which aligns with data mining's goal of discovering generalizable patterns. The core research problem is that graphs contain both node attributes and structural connections. A useful pre-training method should learn both simultaneously. However, most existing approaches capture only one, either attributes or structure. This limitation motivates the need for a framework that can jointly model both modalities during pre-training. The proposed method is a generative pre-training framework with several key components. First, a pre-processing pipeline separates node roles to prevent information leakage. Second, the model performs self-supervised attribute reconstruction by predicting masked features using neighborhood context. Third, it conducts generative structural edge prediction with a contrastive scoring mechanism. Together with architectural innovations, these components allow GPT-GNN to jointly learn attribute patterns and structural dependencies from unlabeled graphs. In the preprocessing pipeline, GPT-GNN uses node separation to avoid information leakage during pre-training. Each node is duplicated into two roles, an attribute generation node with masked features, and an edge generation node that retains the original attributes. Only the edge generation node participates in message passing, while the attribute generation node uses the shared mask vector. This separation prevents the model from indirectly accessing true features when reconstructing attributes, making the generative tasks valid. For attribute reconstruction, the model masks part of a node's features and predicts them using neighborhood information. The masked node receives a shared initialization vector and, after message passing, its embedding is passed to an attribute decoder. The decoder can be an MLP for vector attributes or an LSTM for text, such as paper titles in OAG. The reconstruction loss compares the generated attributes to the originals, enabling the model to learn semantic patterns in a self-supervised way. For structural pre-training, GPT-GNN performs masked edge prediction. A subset of edges is removed, and the model must decide whether each masked edge should exist. After message passing, embeddings of edge generation nodes are fed into a pairwise scoring function to compare candidates. A contrastive loss pushes positive edges to score higher than negatives sampled from unconnected nodes. This task allows the model to capture structural dependencies and learn how nodes should connect based on context. Across experiments on OAG and Amazon, GPT-GNN consistently outperforms all pre-training baselines. Attribute-only and edge-only versions improve performance, but the full model with both tasks performs best. Its biggest advantage appears when labeled data is scarce, showing that generative pre-training effectively captures transferable semantic and structural patterns from large unlabeled graphs. The first strength is novelty. GPT-GNN is the first scalable generative pre-training framework for GNNs that jointly learns node attributes and graph structure. Earlier approaches captured only one modality. By using dependency-aware modeling and node separation, GPT-GNN integrates both, marking a clear step forward for graph pre-training. The second strength is soundness. The framework is well-designed and well-validated. Node separation prevents information leakage and ensures meaningful generative tasks. The decoders match the attribute and edge generation objectives, and the contrastive loss aligns with structural prediction. Ablation studies across datasets show each component, attribute generation, edge generation, node separation, and adaptive sampling, contributes to the final performance, proving the design is coherent and necessary. The third strength is significance. GPT-GNN brings the pre-trained fine-tuned paradigm into GNNs, similar to how BERT and GPT transformed NLP. Because many real graphs are large and sparsely labeled, learning from unlabeled data has strong practical value. This work opens the door for future research in graph pre-training, giving it impact beyond the simplicity of the model. Although GPT-GNN offers a strong pre-training framework, it still has limitations. The generative tasks are relatively simple. Attribute generation mainly reconstructs vectors and cannot model richer or more complex semantics. Edge generation relies on pairwise scoring only and does not capture higher-order structural patterns, such as motifs or communities. Improvements include designing attribute generators that can model richer semantic information, such as text or multimodal inputs. Also, expanding edge generation beyond pairwise scoring to capture higher-order structures could further improve the model's expressiveness. My first question is about attribute generation. The current design mainly reconstructs vector representations. Can the framework be extended to handle more complex attributes, such as full text or multimodal inputs? This is important because many real-world graphs contain attributes far richer than numeric vectors. My second question concerns cross-domain generalization. The paper tests field and time transfer, but not cross-domain transfer. Understanding whether a pre-trained GNN can generalize to graphs with different distributions is important for evaluating the true generality of the learned representations. My last question relates to computational efficiency. Pre-training on OAG and Amazon requires substantial GPU time. I would like to know the practical cost and whether the authors see ways to reduce this overhead, since scalability affects whether the model can be adopted in real applications. In conclusion, GPT-GNN brings generative pre-training to the graph domain, enabling the model to learn both semantic attributes and structural dependencies from large and labeled graphs. Through attribute generation, edge generation, node separation, and adaptive sampling, it achieves strong gains in low-label settings. From a data mining perspective, it serves as a self-supervised approach for discovering transferable graph patterns. Overall, this work marks an important step toward a pre-trained fine-tuned paradigm for GNNs. We are Group 10. Thank you for listening. We hope today's presentation showed that data mining is not just extracting data, but learning patterns, structures, and generalizable representations from large-scale datasets. We look forward to seeing how these ideas inspire future work in AI, 3D vision, and graph models.